All right, everybody, welcome back to page 3 of the law of sines, where this time we're going to be talking about the ambiguous case. Now, with the law of sines, what we're going to be looking at is if we have a side-side angle triangle. If you remember from geometry, we never wrote it backwards because it spells bad word. But we kind of tied that together with, okay, this is not a congruence, so don't do it. With a side-side triangle, we typically will have three different situations occurring. When we say angles or side-side angle, let me kind of write it this way, side-side angle. When we're looking at those three parts, we could have a triangle that's not actually going to be formed. Another situation is if, when we have our side-side angle, please notice that angle A and side B are consistent with both of these. In this situation, that side is long enough to produce only one triangle, where in our third situation where we have side-side angle, if you notice, this side right here also could form a second triangle. Our two triangles are going to be either this obtuse triangle, or, let me change colors on you, this acute triangle. So how do we know which one's going to occur? If you notice right here, I have a GeoGebra app that I have linked to my notes. I'm going to go ahead on my computer, take a look at that, and I encourage you to also play with this app so you can see what different situations are going to be occurring. So if you take a look at this third side, which is what I'm moving, if that third side is too short, we don't even get a triangle. There comes a moment where we could produce a 90-degree angle or right triangle. That's close enough. So if this is at a certain length, two triangles will be produced. And if it goes too far, then suddenly there's only going to be one triangle that we know is guaranteed to be produced. Now, if you notice the relationship between side A here, which is this side that I've been manipulating, that if you notice as it gets closer and closer to that 21.1, that is really at that moment of where the triangles start going from one triangle to two triangles. So one of the key things we are going to be looking for is based off of this angle right here, this 38 degrees. So, or now this 43 degrees. This angle, this side, and this side, if the adjacent side to the angle is bigger than the opposite side, we potentially have two triangles or no triangles. Now, if it's substantially long enough, meaning it forms this one's an isosceles triangle, but if it gets bigger than that isosceles triangle, then we're going to have just a single triangle. How do we officially know which one it is? We do have a way that we could take a look at it and say, numerically, let's go ahead and find our unknown angle. If it's not possible, there's not going to be a triangle. For instance, if we take a look at this triangle here, I will use the law of sines on it. And if we say the sine of 36 over its opposite side of 9.5 equals the sine of, there is no actual angle B here, the sine of B over 22. If I solve for B, B would equal the inverse sine of 22 times the sine of 36 all over 9.5. Let's throw that into the calculator. If we take the inverse sine, which is right here, the inverse sine of 22 times the sine of 36 and divide that by 9.5. What ends up happening is the calculator says it's undefined because it's not possible. If we take a look at this situation, we can rewrite all the information. The only thing we're going to replace is, instead of 9.5 here, we're going to replace it with 14.7. So let me cut to the chase and say angle B now is going to be the inverse sine of 22 sine 36 all over 14.7. And if you notice, let's go ahead and put that in the calculator. I'm going to do a shortcut and replace the 9.5 with 14.7. We get that 61.6 degree angle that you see there. But notice that I also could have it supplement 180 minus that 61.0 or 6 degrees. That supplement could also potentially form a triangle. So that's our ambiguous case. We don't know which one specifically is going to occur, but something that we want to look for. Did not mean to do that as a full screen. Sorry about that. What we are going to be looking for is just kind of like a guidance for us. If we take a look at the side adjacent to the angle, then that side adjacent to the angle, if it's larger than the other side, it's potential for us to have either zero or two triangles. Which one is it? Let's go ahead and find out. So let's take a look at our first problem. Side B, I'm given side B, I'm given angle B, and I'm given side C. So I typically just draw all of my situations out in the same horizontal format, where the angle I'm given is a 40-degree angle. Its opposite side is 4, and its adjacent side is 3. I know that this is not drawn to scale. I'm not as worried about drawing to scale as much as I would love to because of the unknown. We're just going to run with it. Now, like always, I do classify what kind of triangle is it. This is the side-side angle triangle. So side-side angle. So that tells me I'm either going to have 0, 1, or 2 cases. Now, if I look at the adjacent side is smaller than the opposite side. So that leads me to believe it's going to be more like scrolled a little bit too far. It's going to be more like this situation right here, this middle one where there's only one triangle. Let's actually go ahead and see if that's true. So if you remember what I did before on part 2's notes, I went ahead and said angle A equals, angle B equals, angle C equals, little a equals, little b equals, and little c equals. We know that little b is, or side B is 4. We know that side C is 3, and we know that angle B is 40 degrees. So which one should we find first? Let's go ahead and find angle C. So to find angle C, we'll use our law of sines. Sine of C over 3 equals sine of 40 over 4. And you end up getting used to the shortcut if I say C is going to be the inverse sine of 3 sine of 40 over 4. Let's go ahead and put that into the calculator. We'll take the inverse sine, excuse me, of 3 sine of 40 and divide that by 4. And once again, I forgot to include a decimal point. So that looks like 28.822 degrees. So C is 28.822 degrees. Now, this sort of makes sense to me. If you remember doing our check that angle C and side C are both smaller than angle B and side B. So we're keeping those ratios consistent. Now, I told you I'm suspicious that this is only one triangle as opposed to 2 triangles. So let me see what happens if we decide to take the supplement of this angle. The supplement of this angle is 151 degrees. If 151 degrees was a possibility, it's 151.178 degrees. If 151 degrees was a possibility, and I added angle B, which is 40 degrees, if you'll notice, I am already above a 180 degrees, which is how many angles are in a triangle. So it tells me I'm only going to have one possible solution. And then I'm just left to find what that solution is. So I'm going to go back up to my calculator and say, okay, I know angle B is the 28.822 degrees. If I add that to 40 degrees, and I take 180 and subtract that value, that leads me to see that, I'm going to do this in a different color now, angle A is 111.178 degrees. And I asked myself, am I expecting side A to be bigger or smaller than any of the other two? And I think it's going to be bigger just because it's the largest angle. So to find angle A, I'm going to go back and say the sine of angle A over, I do know that angle A is 111.178 degrees. Technology glitch. 111.178 degrees. So the sine of that over A equals the sine of 40 over 4. And in this case, when I solve for A ends up being 4 times the sine of 111.178 over the sine of 40. Let's go ahead and throw that into the calculator. So 4 sine of that angle and divide it by the sine of 40. And I get 5.803 as a length, 5.803. Therefore, my, as I guessed, this largest angle produced the largest side. So I'm fairly confident that my answer is correct. And all of that time just to do one problem. I'm excited. Are you excited? Of course you are, because this is pre-calculus, and pre-calculus is awesome. So let's take the opportunity with the next problem. I'm going to go back to blue. If I have angle A is a 50-degree angle, so 50 degrees, side A is 5. So the opposite side is 5. I will say side B is 10. I really could have put that angle B in either spot. I tend to prefer this orientation just because it's consistent with what I see up here. Sometimes it's very hard to maintain that consistency in my mind as I work through these problems, so I just like to have a consistent format. Quick check, side-side angle, triangle. Because this is a side-side angle, I have 0, 1, or 2 possibilities. So let's take a look and say A equals, B equals, C equals. I know that A is 50 degrees. I don't know B, I don't know C. Side A is 5, side B is 10, side C is unknown. Let me change colors. So the first thing I'm going to find is angle B. So the sine of B over 10 equals the sine of 50 over 5. And shortcut like before, B is going to be the inverse sine of 10 sine of 50 over 5. So B is the inverse sine of that. Let's go ahead and throw that into the calculator and see what happens. Trig, inverse sine of 10 sine of 50, and then divide that by 5. What happens? Domain error. Actually, domain error. What does domain error mean? Oh, this isn't a triangle. And I should know that just because, so this does not exist. I should know that in retrospect, if I think about it, B is the inverse sine of 2 times the sine of 50. If you remember, the domain of the inverse sine is -1 to 1. And since the domain of the inverse sine is -1 to 1, this expression right here is above 1. And I know it's above 1 because the sine of 30 is 1/2. So it's that 30-degree angle that would be the largest angle that I could possibly have in order to make the situation work. So this is not a triangle. No triangle. No triangle. Which sad on one level, but that means that I can go through more problems. So if you're guessing that, okay, problem number 5 had one solution, problem number 6 had no solutions, problem number 7 most likely is going to have 2 solutions, just because that's the way that I roll. Let's go ahead and start drawing. And again, I like to put my orientation where there's my 35-degree angle. That is angle A. The opposite side is 6, and the adjacent side is 8. And if you remember that useful thought that I pointed out to you, that if you see that 8 is bigger than 6, that's kind of a situation where we can possibly have this side being 6 also, forming 2 different triangles. Now, is that guaranteed? No, it's not guaranteed, but the likelihood of that occurring is pretty big. So I have my side angle. Therefore, A equals, in this case, A is 35 degrees. I know side A is 6. I don't know angle B. I know side B, and side B is 8. I don't know angle C, and I don't know side C. Now, because this is a situation where we could potentially have 2 triangles, one triangle being the solid one that I drew, and then one triangle being the dashed line that I have there, what I am going to do is I'm going to label this A1, B1, and C1. And I am considering that there's going to be a possibility of a second triangle, so A2, which that's also 35 degrees. Little A2 is 6. B2, I don't know still. Little B2 is 8. C2, I don't know. And little side C, 3, 2. I don't know that one either. So let's get started with our law of sines. If I take the sine of B over 8, that equals the sine of 35 over 6, which leaves B to be the inverse sine of 8 sine 35 over 6. Let's go ahead, throw that into the calculator. Inverse sine of 8 sine 35 divided by 6. Let me put the decimal point in there. And that leaves me with angle B as 49.886 degrees. Now, I told you there's a possibility for a second triangle, and for this situation there actually is. I'm going to go ahead and do the second triangle in a different color. So I started by saying that's 49.886 degrees. I asked myself, what is the supplement of that angle? So what is, our B could also be 180 minus 49.886. Throw that in the calculator so we don't make a dumb mistake, which is very likely. So that gives me 130.114 degrees as my second angle B. So 130.114 degrees. Now, quick check. If I add 130.114 to 35, that leads me with 165.114. 165.114. And if I subtract it from 180, so 180 minus that answer, gives me this angle is 14.886 degrees, which the fact that I have an angle that shows up here, the fact that angle A2 and B2 together don't go above 180 degrees, that tells me I'm definitively going to have a second triangle. Remember, it was kind of prompted by the idea that the adjacent side is larger than the opposite side. So where do I go from here? Well, since I'm already working with that teal color, let me go ahead and finish solving this teal, or the second triangle. So I'm going to take, let's do the reciprocal identity. So let's do C2 over the sine of the 14.886 equals Now I have the choice of either using B or A. The preference is most definitely to use A. First, it doesn't have the nasty numbers, but second and more importantly, we did not create those. Those were part of the original problem. So therefore, we want to keep what's given just in case we made a mistake somewhere. So that would be 8 over the sine of 35. So my C2 would equal 8 sine of the 14.886 over the sine of 35. Let's throw that into the calculator. 8 sine of, this is where I'm going to scroll up and take that answer. We don't round until the very end. We divide that by the sine of 35. And we get 3.583. So 3.583. Just doing a quick check to make sure that I haven't made any small mistakes anywhere. And I actually did make a mistake. Something didn't seem right to me. This should not have been an 8. That should have been a 6, which does change our answer. And sorry for the mistake, guys. I knew it was bound to happen sometimes. So there we go. That answer looks a little bit more like what I was looking for, 2.687. 2.687. So there's our second triangle. We do have to go and finish solving for that very first triangle. So what I'm going to do first is add 35. And I take 35 plus, I'm going to scroll all the way up until I get to that 49.886 and take 180 minus that result, giving me 95.114. That would be my C1. And kind of like before, I'm going to say my side C1 over the sine of 95.114 equals 6 over the sine of 35. So C1 is 6 sine of 95.114 over the sine of 35. Throw that into the calculator. 6 sine of solution divided by the sine of 35, 10.419. And doing a quick check in triangle number 1, I have the largest angle here with the largest side. I have the medium angle here with the medium side. And I have the smallest angle here with the smallest side. Going back to triangle number 2, the largest angle with the largest side, middle, middle, smallest, smallest. Now, how did I know that I made some sort of mistake? The fact that that angle was so small, that told me, considering that's a 14-degree angle versus a 35-degree angle, that told me that it probably wasn't bigger than 3. I know that all of that doesn't exactly match up, but the more you work with these, the more likely you are to see it. And similarly, we can do the exact same thing with the next triangle. Because I gave one of each, this one is truly an unknown. Is it going to be 0? Is it going to be 1? Or is it going to be 2? Let's go ahead and draw to begin. So I will draw out. As I said, I'd like to always have this angle here just so I can keep the orientation. Side B is 4. So let's call that 4. And then side C is 6. Okay, we said that the adjacent side is bigger than the opposite side. That leads me to think, oh, I'm probably going to have that second triangle. And in fact, I do. So let's go ahead and set up our situation. I don't know angle A. I do know angle B is 20. I don't know angle C. Side A is, I don't know. Side B is 4. Side C is 6. And because we're going to have two triangles here, we're going to label those all 1s. And then we're going to have triangle 2, A2, B2, C2. 20 degrees. C2 unknown. Little a2, don't know. Little b2 is 4. Little c2 is 6. All right, so change colors. And my first thing I need to do, we need to find angle C. So sine of C over 6 will equal the sine of 20 over 4. So C is going to be the inverse sine of 6 sine of 20 over 4. Throw that into the calculator. Trig inverse sine 6 sine 20 and divide that by 4. And I forgot to put a decimal spot or decimal point. So my first C is going to be 30.866 degrees. So that's my C1. I'm going to have a second one where C2 is 180 minus that 30.866. 180 minus that answer is 149.134. 149.134. If I add it to 20, that gives me 169.134. I definitively have a second triangle. If I take 180 minus 149 minus the 20-degree angle, it's angle B. That leaves angle A as 10.866 degrees. And if we solve this triangle, to cut to the chase, if we solve this triangle just like we did before, we should get A2 is 2.205. And going back up to the first triangle, 180 minus the 30.866 minus the 20 degrees will give me 129.134. I hope you're pretty familiar with this, giving us a 1 as 9.072. You could double check yourself to see that that is actually correct. I'm just making it short because I feel like we've done this process over and over and over again, because it really is the exact same process. The trick is kind of looking through it saying, what do we have? What are we given? Take what's given and work with it. Last but not least, we have a story problem. Station Zulu is located 120 miles due west of Station X-ray. So what that leads me to do is to create this to say Station Zulu is 120 miles due west. We know that's north, south, east, west. So Station Zulu is 120 miles due west of Station X-ray. I'm going to label that as an X. A ship sends an SOS that's received by each station from Zulu. So from Zulu, the ship is at a bearing of 40 degrees east of north. So let me draw about a 40-degree angle here, east of north. From Station X-ray, the ship is at a bearing of 30 degrees west of north. I think I need to extend this a little bit further, and I'm going to cheat by bring this down so I can draw it a little bit more accurately. Well, accuracy is not 100% necessary. It tends to help. So this is my 30 degrees west of north. Where do I go from here? How far is the station from each ship? So, or sorry, how far is each station from the ship? The ship I'm going to call S. Let's see. We know that these are 90-degree angles. So if this is a 40-degree angle, this has to be a 50-degree angle right here. And if that's a 30-degree angle, that's a 60-degree angle here. Really, we are solving the triangle. So that leaves 60 plus 50 is 110. If I take 180 minus 110, that leaves me with a 70-degree angle right here. And if I want to solve, I'm going to call this, I normally would call that X. I'm going to call that Z just because that's the distance from Zulu to the ship. I'm going to call this X because that's the distance from X-ray to the ship. And so I'm going to break my own personal protocol, but that's okay because it makes more sense doing this. So what kind of triangle do I have to work with? I have an angle, side, angle. Because this is an angle, side, angle triangle, I'm not too worried about the ambiguous case showing up. So I'm just going to solve this like normal. If I take the X over the sine of 50, that should equal 120 over the sine of 70. So X is 120 sine of 50 over the sine of 70. Throw that into the calculator. 120 sine of 50. And I divide that by the sine of 70. That gives me 97.825 miles. So X is 97.825 miles. And then let me go ahead and change color on you. Z over the sine of 60 equals 120 over the sine of 70. So Z is 120 sine of 60 over sine of 70. And if you'll notice, that's very similar to what I already have in here. So I'm just going to change that 50 to a 60. And I get 110.593. So 110.593 miles. All right. So the ship is closer to station X-ray. So if a helicopter is sent from one station flying at 200 miles per hour, so we are flying at 200 miles per hour, how long will it take to send the helicopter to the ship from the nearest station? So if you remember that distance equals rate times time, our goal is to solve for time. So time is going to be the distance over the rate. Now my distance is in miles, and my rate is in miles per hour. So if we use dimensional analysis, that leaves me with a unit of hours. So let's take that 200. Our time is going to be the 200 miles per hour. If we divide it by the shorter distance, which is the 97.825 miles, this is miles per hour. And really quick, I'm solving for time, which is distance over rate. I was going to say something wasn't quite matching up. Dimensional analysis actually has a use. Let's go ahead and rewrite that. So our time is going to be our distance, which is the 97.825 over the rate, which is the 200. It makes a little bit more sense to me now that if we divide it by 200, it's going to give me 0.489 hours. That's my unit. Now, if I really wanted to say, okay, that's how many hours, that's less than half an hour, so that's going to be less than 30 minutes. If you remember way back to chapter 6, where we worked with degrees, minutes, seconds, this kind of situation is going to be very, very similar. We're going to take our answer, multiply it by 60, And so by multiplying by 60, this means I have 29.3475 minutes. So if I take that, subtract the 29, oops, let's subtract 20 again. My 2 apparently is not working. And I'm doing that too quickly. That minus 29, there we go. So I left with that many minutes. If I multiply it by 60, I'm left with 20.8481 seconds. So this is 29 minutes, 20.8481 seconds. I would have been okay with a 0.489 hours, but just for fun and just to bring back some Chapter 6 material. Hope you enjoyed this presentation on the law of sines. It definitely was a long one, especially when we talk about the ambiguous case. The work can get somewhat tedious at times, but at the same time, knowing that really you're doing the same kind of problems over and over again, a lot of the same practice, and you find that you'll get very fluent with it. So I am signing off. Remember, I've got your back. You've got your back. Have a good one, guys. Bye.